Okay, so I'm going to do chapter 4, problem 23. And in this question, we have a firework that explodes at height h into a bunch of small particles that all have the same velocity. And we need to figure out the minimum angle that these particles could hit the ground at. So to solve this problem, I found the velocity that it'll hit the ground at in the y direction and the x direction. So for the y direction, I use the equation v final squared minus v initial squared is equal to 2ax. So this means that v final y squared, which is the velocity in the y direction which will hit the ground at, minus v initial squared sine squared theta, which is the initial velocity in the y direction, is equal to 2gy. And in this problem, I'm taking the downwards y direction to be positive. So that means that this term stays positive. So then moving this term over to the other side and taking the square root, we get the velocity final in the y direction is equal to the square root of 2gh plus vi squared sine squared theta. And then for the x direction, the final velocity is simply equal to the initial velocity in the x direction because there's no acceleration. So it's just equal to vi cosine theta. So then we have the angle which it hits the ground at is equal to the inverse tangent of the velocity in the y direction divided by the velocity in the x direction. And this could be seen here where the particle has a velocity in the x direction and also in the y direction. So the angle that it hits the ground at with respect to the x-axis will be the inverse tangent of vy over vx. So then substituting in the values we found, we get that the theta that it hits the ground at is equal to the inverse tangent of the square root of 2gh plus vi squared times sine squared theta all over vi cosine theta. And so for here, this term will always be positive because 2gh is positive, vi sine squared theta, these terms are squared, so they'll be positive. And then v initial is positive, and cosine theta, right now I'm only looking at particles flying on this side because the minimum angle will be the same as the minimum angle for the particles on this side. So then if this term is always positive, then we could look at the graph of inverse tangent. And so this is the graph of inverse tangent, and we only have to look at the positive part. So we could see that to minimize theta ground, which would be the y-axis, we need to minimize the portion on the x-axis. So we would need to minimize this portion over here. So then to minimize this, which we found earlier, the square root of 2gh plus vi squared times sine squared theta over vi squared cosine squared theta. So here I just included the vi cosine theta in the square root. So the minimum of this occurs when theta is equal to 0. And this is because when theta is equal to 0, cosine theta is at its maximum. So the denominator is at its maximum, whereas sine theta is 0. So that means that the numerator will be at its minimum. So because the numerator is at its minimum and the denominator is at its maximum, then theta ground will be minimized. So then plugging in theta equals 0 to this equation, we end up with it's equal to the inverse tangent of 2gh over vi squared because cosine squared theta equals 1 and sine squared theta equals 0. So that we could get for our answer that the minimum angle that it hits the ground with is equal to the inverse tangent of 2gh over the initial velocity.